Hi, welcome back. We're going to be doing chapter 7, which is again further reactions of haloalkanes. Last video was on SN1, and then this video is primarily going to be about E1 because I think E2 is a little bit more complicated to explain, and there's a lot of other stuff to go along with the elimination reactions. So just to give you a recap of what we learned so far, we've learned 2 reactions so far, actually 3. One is the radical halogenation. If you remember, we treat an alkane plus a dihalogen, it can be any halogen, and we react it under UV light or X-ray or heat or light or whatever, and then we get a haloalkane, and with that haloalkane, we can then react it in either an SN1 or an SN2 reaction, okay? SN2 reactions occur one step. The leaving group leaves as well as the nucleophile attacks the electrophile at the same time. There's a stereochemistry inversion if there is a stereo center. It requires a good nucleophile. Remember, the left of the periodic table is a good nucleophile, and down below, as you go down, it's a good nucleophile. It requires an unhindered electrophile, so it tends to go to methyls, and then primary, secondary, tertiary. These two are really rare, like I said. It requires a good leaving group, which is a weak base, an aprotic solvent, and the rate is given by the concentration of the nucleophile as well as the concentration of the electrophile. Okay, and then we have SN1 reactions, which are 2 major steps. You can argue that it's 3 with the carbocation intermediate, but I like to think of it as 2 major steps. It forms a racemic mixture, so it's a 50-50 mixture of either a wedge or a dash. It doesn't matter what the nucleophile is, it can be weak or strong. It forms a carbocation and it's stabilized by uh, a tertiary carbon is better than a secondary, which is better than the primary and then better than the methyl. So if you look at it's the exact opposite where SN2 requires an unhindered, but SN1 requires a hindered, if you want to call it. Like SN2, it requires a good leaving group, but it um, it it favors protic solvents better, and we'll get into that in a bit. I didn't say this in my last video, and I apologize, but I'm going to get into that now because we're doing E1 as well. And then the rate is only given by your electrophile, right? And we were talking about that in our last video. So let's see why SN1 favors protic solvents. Um, so first, I have, again, the same reaction. This is going to be an SN1 mechanism, right? We have a tertiary carbon, and we have a ethanol as our nucleophile, which is a weak nucleophile, right? Because it's a weak nucleophile, and because we have a tertiary carbon and a good leaving group, we can assume that it is going to be an SN1 reaction, okay? Now, because it's an SN1 reaction, the leaving group leaves first. I'll denote that by the arrow. Leaving group leaves first. And then we form a carbocation intermediate, right? This is a carbocation intermediate. And we also have the chlorine as a negative charge, as well as our ethanol is still there. Okay, so let's see why uh, protic solvents are better for SN1 reactions. You remember protic solvents, like the one here I've shown is ethanol, they can form hydrogen bonds, right? But if we have an aprotic solvent up here, which is diethyl ether, they're not able to form hydrogen bonds. So if I'm a solvent and I'm able to form hydrogen bonds with other electronegative elements, I have an electronegative chlorine here, and I also have a positive here. Because I'm a protic solvent, I can stabilize this negative charge with the chlorine by my hydrogen, and I can also stabilize this carbocation intermediate even further because now I have the ability to donate my electron density here, right? But if I'm an aprotic solvent, I can't hydrogen bond to make my leaving group stable, and I can't hydrogen bond and donate my electron density to my carbocation, which is, even though this is a good carbocation, the fact that I'm able to donate some of my electron density here makes it even more stable, which is why in an SN1 reactions, because we form a carbocation and the leaving group left, and we have this two in the reaction beaker, this is why we want protic solvents, because protic solvents can hydrogen bond with my electronegative leaving group, making this more stable, and I have the ability and the chance to donate my electron density to this carbocation. Okay, so that's why in SN1 reactions we prefer proton solvents that can form hydrogen bonds. Okay, so let's go into a few practice problems. This is going to be testing if you know which reactions are going to be SN1 or SN2. And I'm going to be testing you on writing your products. Well, I'm actually going to be doing it, but I hope that you can do this at home too or wherever you're at. So here we have uh, nitrogen as a negative charge. We call this an azide ion. This is a good nucleophile, right? If we follow the nucleophilicity rules, it's to the left of the periodic table. It has a negative charge and it's good. What do we have here? We have this carbon is bonded to 1, 2, 3, so it's a tertiary carbon. I know right away it's going to be an SN1, but let's just keep going. We have a tosylate as our leaving group. Remember our good leaving groups, the sulfonate groups. And we also have a protic solvent, a solvent that can hydrogen bond. So I know this is going to be an SN1 reaction. And we also have to be careful because we realize that this carbon is a stereocenter. So because it's a stereocenter and because it's an SN1 reaction, we make a racemic mixture where the N3 can either be on a dash, and we still have the methyl there, or we have the N3 as a wedge, and the methyl is on the dash, right? So a racemic mixture where it can either attack it from the front side or from the back side. It doesn't matter because we form this carbocation intermediate because this tosylate leaves first, and we have this carbocation right here with the methyl group sticking out. If we look left, it's still a tertiary. If we look right, it's a secondary, so we're good where we're at. There's no hydride shifts, there's no alkyl shifts, there's no methyl ring shifts. So because of this, because we form a carbocation intermediate, this can attack it from the front, either the front, making it a wedged, or the backside, making it a dash, right? And these will occur 50-50, okay? So let's look at this. I didn't give you a solvent. I'm just trying to see how you all do with just this. So we have water as our one of our reactants, and we also have this benzene cyclohexane ring, right? So I see a good leaving group here in bromine. I see a secondary carbon here, but I also see a bad nucleophile, right? So this is what I meant by it rarely occurs on a secondary carbon, but, sorry. This is what I mean by it's really easy to spot if it's an SN1 or if it's an SN2. Because we have a weak nucleophile and a secondary carbon and a good leaving group, it checks off all the boxes of an SN1 reaction because this nucleophile is not strong enough to handle one, the steric hindrance here, and two, it's not strong enough to attack a secondary carbon. So this is also an SN1 reaction. I'm going to write that down here. This is also an SN1 reaction where the bromine leaves, right? And we form, after some time, we form an OH here, or it can also be on a wedge because it is an SN1 reaction, right? Or a wedge, right? And this is also SN1. And then we, the other products don't really matter, but we have an HBr here. And in this case, we have a, yeah, we don't have any byproducts, okay? So let's move on to this one. We have a secondary carbon right here. We have a good leaving group and we have a really, really strong nucleophile, right? In this case, a lot of things can happen. You can either say it happens SN1 or SN2. It really depends on our solvent here. But in this case, we're going to go with SN2 just because even though this is a secondary carbon, it looks unhindered right here as compared to this. And we also have a very strong nucleophile, which can take on that. Later on, I will show you a chart telling you if it's SN1, SN2, E1, E2, but I just want you to look at these and just be familiar with how you're going to be um, guessing the products, okay? So it's going to attack backside here while this group leaves, right? Instead of the leaving group leaving first. And because of this, it's attacking from the backside, so we have to flip the carbon. We have to flip it, and we also have a BR here, okay? So this, in this case, this was an SN2 reaction, okay? So let's move on to elimination. So I hope this was able to help. We have SN1, SN1, and then SN2. Okay, so now let's move on to elimination reaction. These are all SN2s and SN1. Now we're really gonna get going with elimination reaction. But before we go to elimination reactions, I just want you to see the subtle differences that are in a nucleophilic substitution and an elimination. Nucleophilic, we have Nu, which is our nucleophile, electrophile leaving group, forming this bond here, substituting the leaving group for the nucleophile. But look at what we have in an elimination reaction. We have a B, which is a base, but we also have an electrophile and a leaving group, but we form this, a double bonded alkane chain, which is known as an alkene, right? So in an elimination reaction, we form an alkene, okay? The easy way I remember this is elimination and alkene, they both have E's, right? But that's the way I like to remember it. But yeah, so in this case, we have a base, but in this case, we have a nucleophile. And does that really, really matter? So let's take a look at what are bases and what are nucleophiles, okay? So first, we're going to go into a refresh on acid-base reactions. If you remember, these are from, I think they're from chapter 2. So we have here, which is going to be our Bronsted-Lowry base, which a Bronsted-Lowry base is anything that accepts a proton being a hydrogen atom, right? And a Bronsted-Lowry acid is anything that that donates a proton, which it's donating a proton here, as you can see. And because of that, we form a conjugate acid, which is directly correlated with our Bronsted-Lowry base, right? You can see the conjugate acid just gained that extra hydrogen. And we form a conjugate base, which is directly correlated to our Bronsted-Lowry acid, which is now doesn't have the H, okay? So this is just a quick refresher. If you're lost on this, please read up on it. This is gonna be important, but I'm gonna go over bases and nucleophiles right now, okay? So basicity versus nucleophilicity, okay? If you remember, nucleophiles are involved in substitution reactions, right? This is the definition of a Lewis base. But bases are involved in accepting a proton, right? Like I said, Bronsted-Lowry base. A negative charge makes a stronger nucleophile. A negative charge makes a stronger base. If you go left of the periodic table, it's a stronger nucleophile, but that's also the same case with a base. It's more basic if you go left of the periodic table. So where's the difference? Where is the biggest differences in determining if something is a nucleophile or a base? It actually comes down to going down the periodic table and steric hindrance. So if you remember from nucleophiles, when you go down the periodic table, it's a stronger nucleophile, right? But if you go down the periodic table, it's less basic. And we can think of this in many ways, but the way I like to think of it is when you go down, let's say you form an acid with iodine, right? Let's compare iodine and fluorine. The acid formed by iodine is much stronger than the acid formed by fluorine. So that means if you have a strong acid, remember acids are ones that have the H, and then what happens in the conjugate base, it loses that H. So let's compare HI versus HF. These are the acids, then the conjugate bases would be I and F, right? Because HI is such a stronger acid than HF, that means their conjugate base is going to be weaker. As you go down, it's weaker. That means my base here is going to be weaker than fluorine. In fact, fluorine is actually a very strong base because my HF is such a weak acid, I make a very, very strong conjugate base. Okay? So as you go down, it's less basic for bases, but as you go down, it's more nucleophilic for nucleophiles. And steric hindrance. So steric hindrance makes worse nucleophiles, right? We don't want steric hindrance on a nucleophile because we're gonna have to attack it. We're gonna have to attack a carbon, right? And it's either backside or front side. And either way, I still don't want any hindrance, right? But in bases, sterics don't really mean anything because I'm only grabbing a proton, I'm only grabbing a hydrogen. I'm not going to get too close to the carbon or the electrophile. I'm just going to be grabbing a hydrogen. So in this case, sterics don't really affect my bases. Okay. So these are the biggest things that you would have to not memorize but know in terms of nucleophiles and bases. Okay. So let's go into a problem. I have these four molecules right here, and let's figure out if they're strong or weak nucleophiles or strong or weak bases, okay? So here we have a two, uh, three is methyl ethyl pro, two propanol right here, right? We have the oxygen. So nucleophiles, like I said, negative charge is a strong nucleophile. There's no negative charge here. Left of the periodic table, this is sort of right. Down the periodic table, this is sort of down. It's kind of down. But steric hindrance, there is a lot of steric hindrance here, as you can see with the methyl groups. So in terms of nucleophiles, this is a weak nucleophile, right? Let's see in terms of bases. Negative charges make stronger bases. We don't have a negative charge. Left of the periodic table is more basic. Right here, we are sort of left of the periodic table, but not really. Down of the periodic table is less basic. We're not, this is sort of down, but not really. And sterics don't affect bases. This is sterically hindered, but it's still a weak base because we don't have any of the promising features of a strong base, which are the negative charges and the left of the periodic table versus down. Okay. And then now we have this terbutoxide ion. Remember, this Na is just a spectator ion to shield that negative charge, but in reality, we do have a negative charge oxygen. Okay, let's see. We have a negative charge. We have a negative charge here. We have down left of the periodic table, it's an oxygen, so it's okay. It's a strong nucleophile. Down, it's okay. It's still an okay nucleophile because of this negative charge that's carrying it. But we have a lot of steric hindrance. Look at this terbutyl group right here. That's hindering it. So in that case, when I said here that sterics don't affect bases, this is a weak nucleophile, but this is a strong base, right? Think of this in an SN2 reaction. Look at how hindered this is. This is not going to be able to attack backside because of this group that's sticking out here, right? And the same thing that goes on with this group right here, which is LDA, where the negative charge is on the nitrogen and this lithium is just being a spectator ion. It follows all the rules of a strong nucleophile, but the only difference is it's sterically hindered, right? Look at these terbutyl groups right here. Oh no, sorry, these isopropyl groups right here. So in the terms of a nucleophile, it's weak. in the terms of a base, it's strong because bases don't care about steric hindrance, okay? And then let's look at this, um, let's look at this, this nitrile element right here. Again, the carbon is on the negative and then this Na is on the plus. So it looks, everything looks promising about a nucleophile, right? It's not hindered, it's not strong, it's left of the periodic table, it's a carbon with a negative charge. So this is a strong nucleophile. And this is actually a trick one. If I don't tell you anything about the pKa's, or if I don't tell you anything about any other of its conjugate acid here, you're not going to be able to figure out if it's a weak base or not. But the pKa of this is around 9.7, okay? And that just means how the pH you need to protonate it. But now I'm telling you that pKa's that are greater than 10 are strong bases, right? So in this case, it's not a strong base, it's a weak base. But I don't expect you to know this for sure, so don't worry about it. I just want you to, firstly, know these two right here and what makes them a weak nucleophile but a strong base. But don't worry too much about this last problem here. Um, it's not, your teacher won't give you anything like that, okay? So let's take a look at the two elimination reactions that we have. We have an E2, which, does that sound familiar? I think it sounds like SN2, right? SN2 was a bimolecular nucleophilic substitution. E2 is a bimolecular elimination. The rate is also given by, in an SN2, is given by the nucleophile and the electrophile. In an E2 is now given as the base, right? We're reacting it with a base. And also the electrophile. Sounds similar, right? This is the reaction mechanism scheme, the general reaction mechanism. We form an alkene, and we also form this base to an H bond right here. And we also have the leaving group. The energy reaction coordinate looks the same. We have this transition state right here where we form the base with the hydrogen as the leaving group leaves. So this is very, very similar to an SN2 reaction, right? So let's take a look at SNE1 now. It's a unimolecular elimination. Sounds similar to SN1, right? And the rate is also given by the electrophile. Okay. We also form a double bond alkene. Remember, elimination forms alkenes, E's and the E's, right? Alkene E1. But we form, if you remember this term, it's called a carbocation, right? We also form a carbocation. So this is very, very similar to an SN1 reaction, okay? In fact, let's see how the reaction mechanism occurs, okay? First of all, I'll give you this methanol with a tertiary carbon and a good leaving group in bromine, right? What happens first in an SN1 reaction? The leaving group leaves. What happens first in an E1 reaction? The leaving group leaves. So let's leave the leaving group. Boom, and then we make this, sorry, I should get rid of these arrows so I can do this with you all. Okay, we form a carbocation, right? We form a carbocation right here, okay? From the leaving group leaving, and then now we're just left with this carbon right here, right? And that's what we have here, okay? We have this methanol still, and then we have this, this carbocation, and then we also have the bromine. So now, how do we form this double bond here? This is where the E1 occurs. This is where the elimination occurs. This is where a base and acid reaction occurs. So we have a Bronsted-Lowry base right here, which can accept a proton, and we also have a Bronsted-Lowry acid right here, which can donate a proton, right? The reason why I can donate a proton is there is an electronegativity difference here, which makes this a delta positive hydrogen, and it makes that one an a partial negative carbon. So what I can do is I can take the hydrogen, right? And this bond between the C to H will go up here. And as it goes up here, it fulfills this carbon's octet, right? Because now I have a positive carbon. If I move the double bond here, I'll have a formal charge of 0. I'll make it a neutral compound, right? And that's exactly what happens in an SN2 reaction. As I get the hydrogen here, this bond between the CH2 to the H, right? This is just a CH3 bond, which is extended out. I just extended it to make it look better for the eyes. As I take the H here, this bond between the C to H goes up to this carbon that was a carbocation, and now I form a alkene. And I also have my leaving group Br, and I also have this H3C with the water group, and that's it. So how do I know which hydrogen to take? You look at the neighboring carbons for its hydrogens. These are called beta protons or neighboring protons. So you look at a neighboring proton, you look at a neighboring carbon, and if that has hydrogens that you can take, that can form an E1 alkene. So because these are all methyls, it doesn't matter if I take it from here or here, they're all going to be the same compound. But you'll see later on that you will have different products, and you will have to determine which one is your major product, okay? So now that you know this, it's very, very similar to an SN1 reaction. SN1, the leaving group leaves, you form a carbocation. You look around to see if there are any hydride shifts. If not, you react it with the methanol, right? If this was an SN1, you would just react this with the methanol, right? But this is an E1, so you're taking the proton here. So how can we tell the difference? Actually, it's not that easy to tell the difference because both are two-step mechanisms. Weak nucleophiles are okay, weak bases are okay. Both need good leaving groups. They both prefer tertiary carbons because of the carbocation, then secondary, then primary, then methyl, and they both prefer protic solvents. So how can we actually tell the difference between an SN1 and an E1? Because it looks like we're just gonna guess which one is the major and which one's gonna occur, right? Actually, in a lab setting, whenever you have an SN1 reaction, there will always be an E1 reaction because of the things that they overlap and because they both require almost the same things. They're gonna happen at the same time. But the SN1 will usually be the major product. It'll usually be the product that's 70% in a reaction versus the E1, which is a minor product, which can even be closer to like 10%, right? So whenever you have an SN1 reaction, there will always be an E1 reaction along with it, okay? There will always be an E1 reaction along with it. But the only difference is the SN1 reaction will typically be the major product, but the E1 reaction will be the minor product. But let's say we want to synthesize something that requires us to have an alkene. We don't want an SN1 reaction, right? So how do we make the elimination the major product? The way we make it a major product is we heat up the reaction. We heat it up to almost like 300 degrees Celsius, and we add minute amounts of acid. What this does is it catalyzes the E1 reaction from occurring. And because of this, this will be our general reaction scheme. We're given a secondary carbon, a good leaving group, right? And we're also given water right here, which is a weak nucleophile and a weak base, right? But we're given H2SO4. If you remember, this is sulfuric acid. And we're also given this triangle looking thing right here, which is just called delta. And it's short for we're adding in heat to the reaction, okay? And because we're adding in heat to the reaction, we're now going to bring forward our E1 reaction rather than our SN1 reaction, okay? So let's see what happens. Leaving group leaves, right? E1 is, okay, sorry about that. I hope this is gonna be a little bit better this time. So we were on how do we make an E1 major? And we said we would heat up the reaction and we would add acid, right? So in an E1 reaction, the leaving group leaves first. We have a acidic condition here, and we have heat, which is also added by this delta. So if that leaving group leaves, we form this carbocation right here. The reason why I messed up is because I added an extra carbon chain right here, which messed the whole thing up. So that's my fault. So because we have this carbocation right here, we look neighboring carbons, right? Which is this carbon, and we look at this carbon. So in this case, the water here, right? The water can either take the proton from this side, or it can take it from this side. And if that happens, we form two separate products. So let's see what happens if the water takes the proton from this side, okay? So the water is gonna take the proton here, and then this bond will go to the carbocation. If it goes to the carbocation, it forms this, right? You can see how that happens right here, where if we number this carbon 1, carbon 2, carbon 3, carbon 4, we take the bond from carbon 2 and we put it to carbon 2, the bond from carbon 2 to carbon 3, right? And then now we have carbon 1, carbon 2, carbon 3, and then now the alkene is on carbon 2 and carbon 3, right? But we can also take it from this other side right here, right? If we take it from this side, it'll go here. Now let's number it. This is carbon 1, carbon 2, carbon 3, carbon 4. Now the alkene will be on carbon 3 and carbon 4, which we get this. And if you compare these two, these are really, really different, right? If you were to name it, this would be 1, 2, 3, 4. So it would be 1, 2, 3, 4. So it would be 2 butene. But if you were to name this one, this would be 1 butene, right? So these are different, very different compounds right here. But there is also another way of getting another product. If you remember about alkenes, is that they have free rotation. So this bond right here can come down. If it comes down, we have them both on the same side, right? Where they were both before on different sides, right? This is called a trans, right? But in this case, they're both on the same side, so this is now called cis. So now because of this, the carbocation was right here. It was right here. You can now grab it from this side or this side, right? And this side here as well. But if you grab it from this side, it's gonna be the same thing as this product, right? What's different is if we now grab the proton from the left side, it'll now come down here and it'll form this, which if you compare it to our first product, it's a lot different, as you can see. This alkane group right here was on top. If you draw it in a Newman, these would be anti, but if you draw these in Newman, these would be staggered and they would be gauche, right? So out of these three reactions, out of these three products right here, which one would you think is our major product, right? So this is a bit tricky to understand, but I gave you a big hint that this was a trans, so they would be anti in a Newman projection, but this is cis, so they would be staggered or gauche in the Newman projections. So it comes down to either this first reaction, this first product, or this one, okay? And I'm gonna tell you the rule now. the rule is the more carbon groups around the alkene, the more stable the alkene is. Okay, so let's see how many carbon groups we have around this alkene right here. Okay, so this alkene appears on carbon 2 and carbon 3. And around these carbon 2 and carbon 3, we have one carbon and two carbons, right? So we have two carbons surrounding this, two carbons. So I'll call that secondary, which is also the same thing that's going on here, right? We have one carbon and two carbon, right? So two. But if we look at this, we're only surrounded by one carbon right here, right? This is the only carbon that's going up because here, these are all H's, right? But if we go here, this is a C. If we go here, these are all H's. So we're only surrounded by one carbon here. And if you actually take a close look at the products, you can see how this is on an edge, which means it's not really substituted, right? Compared to this, which is in the middle, and compared to this, which is also in the middle. But you can also take a look at the amount of carbons it's attached to. Even though this is attached to one carbon, there's nothing else coming down here. These are all just H's. In this case, we're attached to one carbon. We're attached to one carbon right here, and we're also attached to another carbon right there. So by taking a look at it and by looking at how many carbons it's surrounded by, you can tell which one is more substituted and therefore which one is more stable. In this case, because I told you this was anti, if you draw it out, this is going to be our major product right here, okay? And this is a key rule in understanding which product is going to be our major. So it's the same thing as looking at this. Let's say we have uh, a benzene ring like that, and we also have a benzene ring like this, right? If you can see how the two E1 reactions would form, then you're doing an amazing job. But let's see this alkene right here, okay? It's surrounded by 1, 2, and then 3 carbons, right? But this alkene is only surrounded by 1 and then 2, right? So you can see how the substituents play a role. But also, if you take a look at this, the double bond is not as exposed as this double bond right here, which means it's going to be more substituted, which means it's more stable, and this is going to be the major product, okay? So I hope that was able to help, and I hope that you all have a good day. I will be posting E2 reactions soon, but I hope this is able to get to your head, okay? I'll see you all next time.